Hi, everybody. So in the next few minutes, I'll be telling you about our effort to build GAROTA. It's an active root of trust for simple embedded systems. This is joint work with Esmerald, Aliaj, and Tsudik from UCI. And again, I'm Irvine from RIT. So before going into what we mean by an active root of trust, let's just briefly define what classic root of trust means. And the classic definition, one of them is what's in the slide, a computing entity with no ancestor entity capable of providing a trustable attestation for the state of it. Or in simpler terms, it's an ideally small piece of a system that you trust without verifying. So there are several examples for this. Most classic example in network security will be in a public key infrastructure, the root CA, the root certificate authority. But more recently, the term was kind of stolen, and we also steal it for this context in this work, to refer to trusted hardware within devices. And there are several types of ROTs, of roots of trust, for storage, measurement, reporting, and they are used to implement different kinds of security services, such as encryption, secure boot, remote attestation, among many others. And the key feature of this kind of platform is that whatever service they offer is supposed to remain secure even if all the software on the main system, except for the root of trust, is compromised. So coming back to our work, the problem that motivates the work is that the realization that most roots of trust are passive. And what we mean by passive is that they're good for proving properties about the system state or proving that a remote device has executed a certain action, but they typically cannot guarantee that a certain state in the system will be reached upon a command, or cannot guarantee that a certain action will be performed. So what we ask is, well, can we build roots of trust that guarantee some kind of availability for trusted code, even under a compromise of all software in the system? And can we guarantee that this kind of desired task is always executed upon a certain trigger, upon a certain event of interest? So for examples of events, you can think about analog inputs such as a sensor value exceeding a threshold, or expiring times if you want to guarantee some kind of task that executes from time to time, like in real-time settings, as discussed in the previous talk. And for this talk, I'm going to be calling this events of interest triggers. So this is our goal when we design GAROTA, is a generalized active root of trust for providing availability guarantees for code execution. And I should say generalized here means that we want to provide these triggers to be whatever arbitrary events to cause execution, and the executable that gets executed upon the trigger should also be configurable. So to make this a little bit more clear, I'll discuss 3 simple use cases for this kind of feature. So first one is, I suppose that you think about a timer-based trigger. So you want to guarantee execution of a certain time-critical, mission-critical task from time to time, similar to what you would want from a real-time operating system, except that in the RTOS case, you have to trust the RTOS. Here, we want to remove trust from software. Second example, you can think about like some kind of sensor device that performs several things. Perhaps it implements some kind of network communication, perhaps it builds some statistics, but we want to make sure that upon a trigger, such as temperature exceeding a threshold, the most safety critical task, which is sounding the alarm, is always executed no matter how compromised the rest of the system is. Or you can think about a third use case where you have some safety critical commands and you want to make sure that a compromised device doesn't ignore this safety critical commands when they're received from a remote controller. So those are the kinds of settings that we think of when we design GAROTA, and we actually use the GAROTA architecture to implement examples for these kinds of settings. So let me go into what is the architecture. And before going into the overview of the architecture, I should say a little bit about the scope of this design, this first design for GAROTA. We choose to go with bare metal, computationally simple anemic devices with no kernel, no memory protections or any type of virtualization such as MMU to support virtual memory and so on. Devices that are designed for low-end, designed for low cost, low power, small size, and so on. They usually run in a few megahertz clocks, single core units, and have a few kilobytes for program memory. And the question is why we go with these devices? Well, these are simple enough devices to model formally and to create a first systematic design. So it seems like a natural first step, a good target for a clean slate active root of trust design. And it turns out that these devices are quite widely used as pieces of larger systems, and they actually implement tasks that could benefit for this kind of active root of trust guarantee. So this is our reason for going with them. The concepts, we hope, can be further extended for higher-end devices in the future. So let's go into the overview. As I said, the trigger should be any event of interest, and what we use here is a system interrupt. So basically, in GAROTA, whatever system interrupt in the unmodified MCU, in the unmodified embedded device, could be configured as a GAROTA trigger. And the main idea is to add trusted hardware to fuse the safety critical interrupt of interest with the correct execution of the ROT's trusted software, of the ROT's TCB. And this feature, sounds simple, but it requires some modifications. But it boils down to two core sub-properties. The first one that we call guaranteed triggering. And basically, what we do to actually guarantee that an event of interest always causes the TCB execution is that we reuse the IRQ support, and we to cause an immediate call to the TCB code as an interrupt trigger, interrupt service routine task. And then on top of that, so basically if you want to configure a trigger, you can configure it in the same way you configure a normal interrupt, but on top of that, we add trusted hardware to protect this configuration. So this configuration involves, for example, interrupt vector tables, interrupt configuration registers, and so on. And we add trusted hardware to make sure that these configurations cannot be modified at runtime by the untrusted part of the software, anything that's outside the root of trust TCB. And besides that, so this means that whenever the trigger happens, it will call the TCB code. But besides that, we need to make sure that once called, this TCB code is authentic, is the one we expect, and that it executes correctly. So this involves another three sub-properties. So we use trusted hardware to make sure that this code is immutable at runtime, that either by CPU or DMA, that we enforce atomicity, so meaning that once this code is called, it needs to be executed until the end, and control invocation to make sure that it is always executed from the beginning and preventing funny things like jumping in the middle of the code to trigger unexpected behavior. So this guaranteed trigger property, we use the hardware to look into these things and monitor to see if they're happening, and we deal with these things in the most simple way, the same way the MCU deals with them, or deals with any exception, which is by resetting the device. But if we just reset the device in a setting where we want to guarantee availability, we're kind of losing the battle, right? So if we reset and we do nothing, we didn't guarantee anything. So the second key feature that we support in GAROTA hardware is what we call retriggering your failure. So once the TCB is triggered, it executes. If it finishes, fine. If it doesn't, we issue a reset. So the missing component here is to make sure that always after reset, GAROTA's hardware will enforce that the TCB implementation, the root of trust code, is always the first to execute. So this is a picture that's worth 1,000 words. On the red part to the right, you have any untrusted apps, and next to it, you have the TCB executable. And the trigger is protected in hardware to make sure that whenever an event of interest happens, the TCB execution kicks in. What could happen as well is that the device resets or there's some kind of malfunction. So in that case, we make sure that upon initialization after a reset, the TCB executable is the first to run, So, if you're malware attacking this device, you have two options. You let the TCB run, you cause a reset. If you cause a reset, TCB runs anyway. Okay? So, big part of this, and one of the points is that we wanted to have a systematic design that can be used as a reference, hopefully. And so we actually specify these things formally using linear temporal logic. We specify these two key properties, guaranteed triggering and retriggering on failure. And then the next step is to axiomatize whatever we expect from the MCU, from what's already in there, and axiomatize what are the additional hardware features that we need from our architecture. So we do this, but we have no clue if this is if the properties that we postulated are enough. So the next step is to use a proof assistant to show that actually the GAROTA hardware properties, when applied to the MCU machine model, imply the high-level properties that we want. This gives us sufficiency for the properties. It doesn't mean our implementation adheres to this property specifications. So the final step is to use a model checker to automatically translate the hardware design from Verilog to a symbolic modular verifier and prove that the implementation has these properties. In a more pictorial description, that's what you have. We design GAROTA as a set of submodules to enforce each of the LTL subproperties, and we combine that with the machine model to enforce the guarantees that we want. And just a tiny bit about the implementation. All the details are in the paper. We designed these submodules as Verilog FSMs. And they work basically by monitoring CPU signals of interest, like the program counter, like which data address is being accessed at a given time for writes and reads, and detect the violations I mentioned before. This is my last slide on the hardware costs. And by the way, I should say this, we compared them to a bunch of architectures, a bunch of roots of trust, targeting the same class of devices, but they're not doing the same thing. They're all of these are passive roots of trust. They're not active. We put it here for a point of comparison. And you see it's not more expensive or anything. It's actually cheaper. And the reason is, well, we reuse the existing interrupt support from the device, and we just add the minimal amount of hardware support needed to protect this trigger action association in GAROTA architecture. So before I conclude, I'll leave you with some pointers to the paper and GAROTA's open source repository, where you can find all of the implementation, the computer proofs, and the toy use cases that I mentioned in the beginning that motivate the GAROTA design. And with that, I'll be happy to take any questions.